while this is loading and everybody's scanning their code, today's lecture is going to be, I don't want to say a little different, but we're going to have another design example, and it's going to be very much like the homework that you just did. So, but the point of the example is to make sure that you all are comfortable with the homework that you just did. What I'll say about this process, and probably this is the case with the last homework that you did, I think it's fair that that's one of the longer homeworks this semester. I think you're probably starting to get the hang of how like these homeworks are formatted and sort of their scope. That's one of the more in-depth assignments that we're going to have in the entire class, and it's also one that's really important. And so I really want to make sure that we're comfortable with that process. And I've taught this class, pretty much every year since I've been here, and I have found that even if it feels like you're just doing it over again, it's worth it, because the more comfortable that you get with the manual, the more comfortable that you get with just the ideas and the process and whatnot, the better, the more smooth things will go later. Because we're going to, right now we have a design process and a step-by-step procedure for tension members. We're going to develop a different but similar step-by-step process for bolted connections, for welded connections, for columns, for beams. And once you get familiar with that idea, it becomes easier to absorb some of the later processes, which actually are a little bit more involved. As an example, we are not really using any design aids right now to select tension members. We're sort of just doing the math and picking a shape. We're going to find with columns and beams that's not possible. And we can't really do it without some of these aids in the later part of the manual. Bless you. So this is going to be a very quick example, but very akin to one that you did on the homework. Then I want to spend the rest of the class talking about block shear. Block shear is different, and I want to give it its time in the spotlight. So just to make sure that we're all sort of on the same page, this is our step-by-step process. We're determining the factored load. We're computing our two design values that we use to select an element, our gross area design limit and our radius of gyration design limit. Now, remember that the gross area design limit is based on assumptions for net section fracture. And so we cannot just select a member and say that we're good. We have to go back and check one. So based on these constraints, we're going to select the lightest shape available based on these two values. And then once we get one, we have to analyze that shape to verify its performance. And really, it's the net section fracture limit state that we're paying attention to. Finally, we are going to summarize the results and compute the efficiency. I'm going to streamline that process a little bit for this problem. So this example that I do today is going to be, how can I put it? I was much more elaborate in my discussion during our last lecture. Today, I'm just going to get right into it. And then don't forget, here's the two limit states that we're looking at: gross section yielding and net section fracture. And I'm going to try and talk about block shear today. All right, so hopefully after this example, I think you can kind of see this is very akin to what you just did on the homework. If there's any questions that you had about the homework that you just did, this example will probably answer them, because it's very much like the one you just did. We're going to select a W12 to resist the following loads: 130 kip dead load and 110 kip live load. Now, we do have a 30-foot long member geometry, so that will allow us to select a member based off slenderness limits. We do have a steel that we're assuming, and we know that we're using 7/8 inch diameter bolts, so a slight mix-up or a slight twist from what we've done in previous problems. We've been using 3/4 inch diameter bolts for most of the problems that we've been doing here. Now, one thing, there is one reason also for doing this problem now, is I kind of want you to think about this problem and how the introduction of a block shear limit state might affect your design later. But we'll get to that here in a bit. Now, before we start getting into our design calculations, so what we'll do is, let me get this back over here. Come on. All right. So before we get into the design, let's make sure we list out some member parameters. So we know the member length is 30 foot long or 360 inches long, okay? We know that we were given A992 steel. So we know that based off of table 2-4 for rolled shapes, we know that FY is what? See if everybody remembers that now.
36.
Not for A992. 50.
That's right.
And we know that FU is what?
65.
65. See, there's sort of another reason for sort of quote unquote repeating this problem. Some of these values are going to start just, coming out by instinct, which is good because it'll make tests go by a lot faster and whatnot. We do, what's that?
I said I just looked at it.
Well, let me tell you something. When we start getting into like March and April, you won't need to look it up. Trust me. It'll come. Like when we start talking about columns and beams, we will only be dealing with 50 KSI steel. We won't deal with anything else. We will only deal with W shapes for columns and beams. So it'll make all that a lot easier. So our bolt diameter is 7/8 of an inch. So what does that make our hole diameter?
1 inch.
1 inch. Okay. All right. So again, making things, hopefully pretty instinctual. Okay. So our first step is to do what? When we're in design mode. Remember, this problem is in design. We're trying to select the W12 section. So what do we need to do first?
Factored loads.
Factored loads. Compute PU. All right, so PU is 1.2 P dead plus 1.6 P live. I think we can look at the numbers and see that's the one that's going to govern. 1.2 times 130 kips plus 1.6 times 110. Okay? And so when we chug that out, what are we going to get? 332. All right? So that's pretty easy. And again, the one thing I want to emphasize is that is easy for this problem because I've given you the loads. It is possible that I don't give you the loads, but I give you the structure. I say, here's a truss. Here's the loads on that truss. We're designing that member. What are the loads on that member? Well, what do? Truss analysis, method of joints, method of sections to get the tensile load in that member. So we are actually going to have a problem like that next week. So you all like trusses, right?
No.
Trust me, it's not bad.
Shoe.
That's enough.
You think that's all the jokes I have? Guys, just brace yourself.
It's not.
That was a good one. Come on. Steel design, brace yourself.
Real good. Classic.
Okay, so we need a gross area for design purposes, and so we're going to do the denominator as the minimum of 0.9 FY and 0.75 squared FU, all under PU, okay? So over here off to the side, 0.9 FY. I think I can do that one in my head. That's 0.9 times 50, so what is that, 45? What is 0.75 squared FU?
36.56.
36.56 KSI. So that's definitely the one that's going to govern. So 332 kips over 36.56 KSI. And so what do we get for that?
9.08.
9.08. Second?
Yep.
And then we need our design, which is L over 300, which is 360 inches over 300. I think I can do that one in my head. I think that one's 1.2. So if we're selecting a shape, okay, so let's wrap our head around that. So we're selecting a shape. What W12 shape should we select that has a gross area of at least 9.08 square inches and has a minimum radius of gyration of 1.2? Has everybody brought their AISE 15th edition steel construction manual, CD 414 steel design? I say that and there's like 2 or 3 people in the class that say, I forgot my manual today. Dr. Mike isn't gonna look at me. Damn, he saw me. I love my job. So what shape should we give a shot?
W12 by 35.
35, okay. Do I have a second on that trial shape?
Yes.
Okay. All right. Now, in order to analyze this trial shape, we're going to need some properties, okay? Now, first off, we know we're going to need the gross area, which I can go ahead and list as 10.3 square inches. The minimum radius of gyration is RY for a W shape, and that is 1.54. Okay? Now, what other properties are we going to need right now before we turn away?
The depth.
The depth, we are going to need the depth.
The flange thickness.
So the depth is, well, let's do the depth first. What is the depth?
12.5 inches.
Okay, we're going to need the flange thickness. And what is the flange thickness?
0.52.
Okay. Anybody know another dimension that we're going to need? You said the depth. There's a dimension that goes along with that.
One part of the WT size.
We're going to get to that here in a bit, but you said something else. What'd you say?
Flange width.
We're going to need the flange width. And the reason that we need BF and D is because of that case for the U value we need for K7. So what is B sub F?
6.56.
6.56. Okay. Now, Mr. Odell was saying, what were you saying?
So the Y bar for a WC shape has the size.
Okay, so what shape? A WT what?
6 by 17.
Okay, so for a WT 6 by 17 and a half, what is Y bar? So basically what I probably ought to do is say that this is from table 1-1 and this is from table 1-8. And so maybe another point I'm making with this lecture is that once you actually start getting right down into it, steel design is a lot more rote than you would think. So that doesn't mean it always is, but there's a lot of stuff in steel design that does get to be pretty rote.
Is it 1.3?
1.3 inches. All right. So that's our trial shape, okay? Now before we move on, let's just make sure we all understand what we're doing in step 4 and step 5. So in step 4, we are analyzing this section, this shape, okay? So we can sort of ignore everything in step 2, right? All step 2 was a roadmap to get us here. We are here, we have our trial shape. So in step 4 and step 5, we are analyzing that trial shape. So if we analyze that trial shape and we find that we have an efficiency greater than 1, what does that mean?
Try again.
Try again. And what does try again mean?
Go up.
Go up a shape. So we go to the W12 by 40. Is that right?
Yeah.
So we would try a W12 by 40, get this property for a WT6 by 20, and just do it all over again. If we do step 4 and step 5 and we have a really over-designed member or a really low efficiency, we go a step down, do it again. So it's just repetitive, okay? Now let's see what we can figure out in step 4. So analyze trial shape. Okay. So we have gross section yielding, net section fracture. Gross section yielding is something we could do right now, but for net section fracture, the first thing we need is the net area, right? And how are we going to compute the net area of this section in this problem? We're going to take the gross area and do what to it?
Subtract the bolt holes.
And how many bolt holes are we subtracting?
Is it 4?
4. So, first off, I was getting ready to write 9.08, and that's wrong. I write 10.3 square inches because that is the area of the shape that I'm looking at. I'm looking at this shape, so I'm dealing with that. 10.03 minus 4. What's the bolt diameter? Or the hole diameter, not the bolt diameter, the hole diameter. 1 times 0.520 inches. Plug and chug, and what do I get for this?
$8.22.
8.22. All right. So there's our net area. Okay. Now we've got our shear lag factors. What cases are we going to have to consider for shear lag?
Would it be the same as the homework?
What?
Would it be the same as the homework for U2, U7?
2 and 7, right? So case 2, case 7. All right. So let's look at case 2.
1 minus X bar.
Yep. And X bar is going to be the Y bar for the WT, which is 1.30 inches. And what is the connection eccentricity going to be? Or sorry, the connection length. What is the connection length for this problem?
8 inches.
8 inches. So what is 1 minus 1.3 over 8?
0.8375.
So we'll say 0.838. All right. Now case 7. Does case 7 apply in this problem? What does case 7 say? It says WMS or HP shape, so we're good there. And it says with flange connected with 3 or more fasteners per line in the direction of loading. Do we have 3 fasteners per line in the direction of loading in this problem? Yes, we do. So this applies. And so how do we handle case 7? What we do is we compare B sub F, which is 6.56 inches. And we compare 2/3 of the depth. And 2/3 of the depth is 2/3 of 12.5. And what is that?
8.3.
8.33. So BF is less than 2/3 of the depth. So what does that mean U7 is?
0.85.
0.85. And from all this hullabaloo, what do we actually use for U? The 0.838 or the 0.85?
U7.
U7, the maximum. So now the analysis becomes pretty easy, right? So we have gross section yielding. And then AG is 10.3. And then net section fracture. So this is 8.22 and 0.85. So what do we get for gross section yielding? 0.9 times 50 times 10.3.
463.5 KSI.
Not KSI, but you're right on the number.
Yeah.
63.5 kips. Because we're taking the KSI, multiplying it times an area there. All right. What about net section fracture?
360.65.
Okay, I'm getting a different number. I got 340.6.
That's what I got to do.
Did you get that? Or? So what I'm going to do here to streamline this a little bit, and instead of computing an efficiency for every one of these, I'm just going to compute the one for the one that governs. Okay. Now I am going to also compute the slenderness. So L over R min is going to be L over RY, which is 360 inches over, what was RY? What was it, 1.54? And so that's 233.8. So yeah, okay. So to summarize, and maybe what I'll do is just sort of, here's what I'll do. Stick that over there, just so I don't have to scroll so much. So to summarize, we know that the factored load on this member was 332 kips, and the capacity that governs is the smaller capacity. And so our PPN is going to be 340.6. So is this a safe design? Yeah, it's a safe design. What is my efficiency for this member?
97.48.
That's I take that grade on acceleration learning. Yeah, so that's a good design. And our L over R is 233.8, so we know it satisfies that. This is a pretty good member. I think that's a winner right there. I want to spend the rest of the time talking about block shear, so I wanted to get through this part pretty quickly. And again, if this number was over 100%, we would just go to the W12 by 40 and redo all this. And keep doing that until we get one that works. So, a question might arise, what's the likelihood that the member fails? That's a good question. The likelihood that the member fails is proportional to how inaccurate that gross area times 0.75 equals the effective net area is. So a good example is if you have really big bolts going through really small material, then yeah, it could be inaccurate. So if our bolt sizes got pretty big, we might need to up our capacity a bit. I can tell you with most tension member designs, if you have to iterate, you might have to iterate once, and that's it. Like if you're having to analyze 3, 4, 5, 6 members to get the right answer, you're probably doing something wrong. So you probably have an error in your calc somewhere. Sound good? All right. I want to spend the rest of lecture today talking about block shear. We're not going to actually do any block shear problems today, but this one's unique, and it's worth kind of its own discussion. All right, but to be clear, any other questions on this? Hopefully this problem was pretty simple based on the homework that we did last time. Okay, let's talk about block shear. Now, what is block shear? The best way of describing what block shear is to actually just show you, okay? So block shear happens when a member fails and it looks like this, okay? So what happens in block shear is that you have let's say a tensile element that is connected via bolts, and what happens is you have this combination of a tensile failure along one plane and a shear failure along another. So if we're talking about this image here on the top right, so this was done, this was an image taken in a lab. One of the things to explain what's going on here, so they basically take lye and they quote unquote paint it on the beam. So that's why it kind of looks like white. And then as the steel yielded, that stuff flakes off, so you can see the yielding pattern on the steel. So if you're wondering, if you ever look at lab tests of steel and you're like, why does the steel look like it's painted white? That's why. Okay. So this is a test in a lab, and you can see that they were yanking on the member like this, and so this end sort of failed in tension because they're yanking on it this way. So this plane is experiencing tension, and this plane here is experiencing shear. So it kind of does that. Okay. So it's a combination of a tensile failure and a shear failure. It's actually kind of discovered by accident. They were doing some lab experiments at a lab in Canada, and they were like, oh, I didn't expect that to happen. And then they did it, and then it happened again. And they're like, oh, okay, I guess this is a thing now. So yeah, so this is the block shear failure phenomenon. These are some more refined 3D finite element models of the phenomenon. And you can see sort of the same idea. Here you can see a tensile failure here, and then a shear failure along this plane here. Does that kind of make sense? That's kind of what block shear is, okay? So, to be clear, this is not something that we're going to quote-unquote design for. And so what I mean by that is we're using right now, we have a design procedure where we use AG design and R design to select a member. And we're going to do the same thing. The only thing that this would affect is that in step 4, we would just have another limit state that we need to check, and that's what block shear is. Okay, so this is sort of a more schematic view of what we're talking about. So, what ends up happening is that under tensile and shear failures, we can sort of have a block of steel that kind of rips out of the member. So that's why we call it block shear. Okay, now I have here a tension member, and I am showing a block shear failure path, and I want to be clear, I am showing you one block shear failure path. We're going to see here in a bit how it is possible under a given tensile member that multiple block shear failure paths are possible. That does not mean that we have to check all of them. A lot of times with block shear, you can kind of use your common sense and see that only one limit state is going to govern, or one block shear failure path is going to govern. That'll become clear when we start looking at the cases. Okay. Now, what's weird about block shear is the spec. Okay. So if you open your AISC 15th edition steel construction manual, I want to point out a couple things. So the first thing I want to point out is we are no longer in Chapter D. Chapter D is the chapter on tension members. We're not in tension member land in this limit state. We're actually in Chapter J in connection land. Okay? Now we're in section J 4.3 on page 16.1-138. I want everybody to turn to this because I want you to see this section in the spec. Okay? And I always like making sure that as we're talking about stuff in the specification that you have a little bit of an understanding on the anatomy of the specification. So chapter J is the chapter on connections, okay? Section J1 is just intro. J2 is on welds, J3 is on bolts. We're in J4, which is the governing strength of connecting elements, right? So that kind of is like where we're at here, because we're not really talking about the bolts. We're talking about the stuff the bolts are connecting, right? So we're talking about the tension members. That's kind of why we're in Chapter J of the specification. All right. Now, I think the first thing that ought to be brought up is the anatomy of the equation, right? So if I just read section J 4.3, it says, and I quote, "The available strength for the limit state of block shear along a shear failure path or paths and a perpendicular tension failure path shall be determined as follows," and then you get this. And the first thing you see is you look at it and go, what the heck is going on here? Because we have the nominal capacity equals this pile of junk such that it's less than or equal to another pile of junk, right? So right off the bat, that arrangement is probably a little weird. The point I want to make is that you're going to start to see expressions like that in the specification. This is not the first time that we're going to see equations written out like this. But what that means, to keep it simple, is that you're just taking the minimum of those two expressions. So you're taking the minimum of the first expression and the second expression. So whenever you see that equation equals a term less than or equal to another term, that's what that means. So I'm rewriting it like this, right? So we have Rn equals this plus this less than or equal to this plus this. It's just the minimum of those two lines. That's my way of clarifying it for the class. And again, we'll see this to come, okay? Now I'm going to do a little bit of algebra to make this a little easier to digest. Let me go back to this slide to sort of explain. So let's take a look at these two lines, okay? So I have Rn equals the minimum of this plus this, or the minimum of this plus this. But look at the equations. These two are the same, right? So what I could do is I could just say it's the minimum of these two plus this term here on the outside. So I can factor that all the way out. And the other thing I can do is I can factor out the 0.6 to make my life a little easier. So instead, I'm going to take this equation out of the spec and sort of rewrite it a little bit to make life a little more easier. And this is going to be the equation that we use. To be clear, there's nothing magical about using the one on the left versus the one on the right. I'm just telling you that the one on the right is going to result in less button crunching on the calculator. Okay? There's another reason that I kind of like the expression on the right, because it actually does, in my opinion, explain the theory of block shear a little more clearly. Okay? Now, when we look at this equation, so keep in mind, this is the most involved limit state equation that we've dealt with this entire semester. I mean, for gross section yielding, it was just 0.9 FYAG, done. For net section fractures, 0.75 FU ANU, done. And then there's this. It's like, whoa, what the heck's going on here? But there's a lot here that should be familiar. First off, there is an FY and an FU. Those are the same that we've been dealing with this whole time. Now, there's a lot of area terms. We have an AGV, an ANT, an ANV, and all that. But I think that based on the notation, you can pretty easily discern what these are. So if I say AGB, that's the gross area in shear. If I say ANT, that's the net area in tension, right? And they are found the same way that we find gross and net areas, you know, for a member in general. We're going to get to here in a bit how we actually compute those. That'll probably be more of a discussion for the next lecture. This isn't going to be on your homework that's due after the next lecture, so don't worry about that. UBS is a block shear reduction coefficient. It is very akin to a shear lag factor, but for 999 times out of 1,000 for the cases that, you know, 990, maybe more like 99 out of 100, the block shear reduction coefficient is going to be 1. I'll show you some cases where it's not, but in most cases it'll be 1. Okay. Now, the nominal resistance, and then, you know, we multiply by our phi value of 0.75, and boom, there we go. Okay. Now, the one thing I really like about this expression is the way it's written with this 0.6. Okay. And I have asked on exams, what's the deal with that 0.6? And invariably what will happen is sometimes students will say, Dr. Mike told me, but I forgot, so I'm going to say it's a factor of safety. And what I'm going to do is say, that sounds good. It's wrong. It's not a factor of safety. Okay? It's not a factor of safety at all. Okay? Now, to explain what this 0.6 term is, takes a little bit of discussion. So this is a perfect chance to talk about this today. How many of you have already had soils? How many of you are in it now? Has the Moore Coulomb failure criterion come up yet? It will. Trust me. For those of you that have had soils, does that look familiar?
Yes.
Does look, okay, good. All right. For those of you that have had soils or have not had soils, let me take a step back and talk a little bit about failure criteria. Okay. So you all, how many of you had me for 216 for deformables? So a lot of you. Okay. So in deformables, one of the things that we did is we looked at this thing called Moore circle. Y'all remember Moore circle, right? Moore circle is you have a stress state, right? And then Moore circle will tell you based on a change of orientation what your new stress state is. And so one of the things that we would do in 216, bless you, is we would say, given a stress state, what's the worst case? What are the principal stresses, maximum shear stresses, et cetera, et cetera. Y'all remember that? Okay. The flip side is to ask, does that stress state satisfy failure criteria? Now, failure criteria becomes a discussion dependent upon the material that you're looking at, okay? For example, one of the most common failure criteria that we as civil engineers use is the Moore Coulomb failure criteria, which is appropriate for brittle materials like soils, okay? So what we will do is we will characterize a soil based on its stress state, based on its cohesion, based on its angle of internal friction, and then we determine whether or not that stress state satisfies a failure criterion or not based on where it falls upon this failure envelope. The equation of that failure envelope is tau equals C plus sigma tan phi. If you haven't heard that yet in soils, you will later. Am I right? What's that? You're on the right track, yes. Now, the Moore Coulomb failure criterion is appropriate for brittle materials. Would we use that for steel? No, we would not use that for steel. For metals or ductile materials, the most common yield criterion is the von Mises yield criterion. And the von Mises yield criterion tends to be an industry standard for a lot of standard, let's say, refined 3D FEA. So I'm going to break out some abacus stuff. Whenever you run an abacus analysis and you ask it to generate stresses at the end, by default it will generate von Mises stresses. And so it will plug those into the von Mises yield criterion and tell you whether or not it fails. You can tell it to do something else, but that's kind of what it does by default. Okay. What is the von Mises yield criterion? Well, in 2 dimensions, like, you know, here's the equation for Moore Coulomb. For von Mises, the equation looks like this, okay? And so basically what you're doing is you're plugging your stress state, remember your sigma x, your sigma y, your tau xy, into that stress state, and you're basically determining how your stresses compare to Fy, right? So, for example, to keep it simple, if you set sigma y equals 0 and you set tau xy equals 0, and so what that would mean is you're just taking an element and you're yanking on it. That's all you're doing. So what would happen is it would yield when, what does this equal? Okay, so sigma y is 0, that's 0, that's 0. So it's just the square root of sigma squared or sigma, right? So what it's saying is it'll yield when the stress equals Fy. Of course, it'll yield when the stress equals Fy. But that's under normal stress, okay? We're talking about block shear. So what happens if you have an element that's under shear, okay? So you take all the normal stresses and set them equal to 0, but leave the shear stress alone. When does an element yield under shear, okay? Well, under normal stresses, it yields when the stress hits Fy. But under shear, it yields when the stress doesn't hit Fy, but it equals Fy over the square root of 3. Now, if you break out your Casio FX115S Plus and ask it what is 1 over the square root of 3, it will tell you it's about 0.5774. And what the building code says is, let's just go with 0.6. Let's just make it simple, right? So the bridge spec will actually use 0.58. So anytime that you see an element related to shear, it will limit the stress to 0.58. In the building spec, they just say, close enough for government work, let's just call it 0.6. So the point I'm making is that this is not the first time this number is going to pop up. We're going to see 0.6 pop up again in a number of different contexts. And what that 0.6 means, it's not a factor of safety. That's not what it is, okay? What it is saying is that if you have an element that is subjected to shear, it will not yield at Fy. It will yield at about 60% of Fy. So it's not a factor of safety. It's representing the mechanics of the situation, okay? Does that make sense? If you wanted a factor of safety, you'd have to apply a factor of safety on top of that, okay? Does that make sense? Okay. So yeah, we'll see that 0.6 pop up a couple different times, and that's where it is. Sometimes it's obvious, sometimes it's not so obvious. Like when we look at bolt bearing, the 0.6 is a little hidden, but it's there. Make sense? So yeah, if you go back to the equation, look at the equation here. So we have UBS, FU, A, and T. So if we're looking at the block shear expression, this is the tensile capacity. Everything that's here is the shear capacity, and everything that's related to shear is multiplied by 0.6. So that's kind of why that's there. All right. Now, I'll go ahead and mention this, the UBS term. Again, you can pretty much say for everything that we do in this class, UBS is 1. Sometimes in steel design, we use what's called a coped beam, C-O-P-E-D. Now, coping a beam involves doing this right here on this top image. So this would be like a framing plan in a building, right? Okay, so imagine the Brad Smith Innovation building that they're doing on 4th Avenue. So there's beams framing into one another, right? So let's say I have a girder going down the floor and I've got floor beams framing in. Well, I can't just connect those directly if I want the floor surface to be flat. So what I'll do near the end of the beam is I'll cut a little bit out of the top so that I can stick the beams together and frame them together. That's called coping, okay? So we do that in steel frame construction so that when beams frame into girders, the floor is flat, okay? If we ever have a coped connection and we have multiple rows of bolts along that coped connection, we use a UBS of 0.5. That's the only time we use a UBS of 0.5. Every other time we use a UBS of 1. And we're not going to deal with any of these types of connections in this class this semester. So you don't need to worry about it. But I throw it out there because I want to educate you as to what that factor is doing. It's basically accounting for non-uniform stress around the connection, much like U for net section fracture. Make sense? All right. Now, this is something that we're going to talk about more in detail on Friday. I'm not going to get too far into the weeds on this. What I can tell you is that we're going to have scenarios where not only do we have to identify the paths themselves, but we have to see which one will govern. I'm not going to spend too much about this today because I've got some schematics of some different scenarios where you can sort of see it in 3 dimensions a little better, and it'll take me a while to pull it up, and we're not even really needing to talk about this today. But whenever we're identifying block shear failure paths, a lot of the rules that we apply are akin to the rules that we apply to net section paths for staggered connections. In other words, when we're looking at block shear, we need to identify paths that leave all the bolts intact, okay? The other thing that we have to do is we have to make sure we identify a path that fully separates the member from the connection, right? So what we can't have is a block that just goes like this, this, and this. Yeah, I mean, that's a path, but these bolts are still connecting it to the adjacent member. But if we're gonna look at block shear, we have to have a path on this block that is actually subjected to shear. In other words, like this path over here on the left has one tensile path and it has 2 paths in shear. Now, I'm sure some of you might ask, well, wait, can't we just fracture it this way and all this rip out? Yeah, we can do that. That's called net section fracture. That's what we've been checking this whole time in net section fracture. There's no internal path in the member that's subjected to shear that's failing under shear. So there's nothing there to necessitate a block shear failure path. Now, for this connection that I've drawn here on the screen, this is a potential path under block shear, but so is this one, okay? This one, so look at this path. All the bolts remain intact. This path is in shear, and if I were to take a pair of scissors and cut this piece out, the member would fully be separated from the connection, right? So the question might be, which one do I check the math of? Do I check this one or this one? Well, the best way of describing it is, which do you think is a longer path? This path that I'm drawing, or just this? Which is longer? One on the left, right? If it's longer, that's more material to rip through. If it's more material to rip through, that's a higher capacity. So which is more likely to fail first? The one on the left or the one on the right? The one on the right, right? Because there's less area to rip through. So you can use a little bit of common sense and go, yeah, this is a potential failure path, this is a potential failure path, but this one's going to result in a lower capacity. But I don't want you to get too worried about identifying those failure paths because, again, I've got some schematics I'm going to show you on Friday that's going to make the identification of those paths a lot easier. And what we're going to be talking about on Friday is not just the high-level identification, but actually the math necessary to compute all of these areas. It's not hard, but you just got to put your thinking cap on and make sure you're paying attention. And we've already done a full example today, and we don't even have time to get into this. So we're going to end it a couple minutes early. I'm going to pull up the code. I will see you all on Friday.